Hey periods 3 and 4. Today we missed part of class, and as a result, you didn't get to do the whole lab. So I made a quick summary of all the lab results put together. If you were assigned part 1 to the lab, you were trying to determine the relationship between wave amplitude and speed. This is a transverse wave. The person's taking their hand and moving its amplitude perpendicular to the direction the wave would travel. To change the amplitude, we would move the hand up and down at different amounts. The easiest way to do this in the lab was to move it half a foot, 1 foot, 1.5 feet, using the grid that's already laid out on the floor with the tiles. Then to measure the speed, you would measure the distance from your hand to the other end, while someone else calculated the time it takes using a stopwatch. Then speed is simply distance divided by time because it travels as a constant speed. In this case, wave amplitude should not affect speed. And the reason I know this is that in real life, wave amplitude, like the loudness of sound, doesn't make sound travel faster. Me whispering doesn't make sound travel slower. With light, if I have a really bright laser or a really dim flashlight, both travel the same speed because the amplitude of the wave has no effect on speed. Just like the amplitude of a simple harmonic oscillator does not change the time period. But what does change it is the tension. Tension changes the medium the wave is traveling through. And the more tension you have, the larger restoring force pulling the spring back to its original position. Think back to this animation here. If I had a stronger spring constant, that slinky would be able to snap back into place faster, thus propagating this wave at a faster rate. It is not a linear relationship here, it's closer to a square root. But in this case, it's a square root function where as tension goes up, speed also increases. Later, we'll study all the different things that affect speed, but primarily the speed depends on the medium it travels through. So traveling through a more tense medium with a larger restoring force will increase the speed. For part 3, we needed to look at interference. Instead of collecting quantitative information where you were taking numerical data, in this time you would take qualitative, just based on your careful observations. In this case, Elsa claims that when waves with amplitudes in opposite directions interfere, it makes a wave whose amplitude is lesser than either of the original two. So, let's use this wave superposition tool. In this case, I'm going to make my blue wave my positive wave, and I'm going to make my orange wave negative. In this case, orange has an amplitude of -1, blue has an amplitude of +3, and notice they both have the same pulse width. They're the same size wave. As these two waves go towards each other, the moment when they overlap, you get a superposition state. You have a smaller wave than you did before. Let's run that one more time. And we'll move the animation speed slowly when they overlap. Maybe a little bit less slowly. If you follow any one particular piece of string, let's say we follow this one, it never reaches that +3 amplitude while the two waves are interfering with each other. That's because wave interference makes it so the resulting wave is smaller than it originally was. In this case, it doesn't reach up to 3 for its amplitude. So it looks like Elsa is right. Having two waves on the opposite side causes them to have destructive interference. Their amplitudes cancel each other out. So, now let's check Anna's claim. Anna claims that when they're on the same side, they temporarily interfere again, but that the waves bounce backward off each other, traveling back the way they came. So I'm going to make blue positive, and I'm going to give it an amplitude of +1. Orange would have an amplitude of +3. And let's run these together. Okay. Notice, pick like any one piece of string here, that goes higher than it originally did. It makes an amplitude higher than the 3. So when two waves go in the same direction, their amplitudes add together. Anna's correct about that, but check this out. I'm going to run it a little bit faster. When the waves bounce off each other, when the waves interfere, they actually don't bounce off each other. Okay? Follow the blue wave. The blue wave is currently traveling to the left. They interfere with each other, and check it out. The blue wave is still traveling to the left. So they don't actually bounce off each other. They just continue traveling as if that interference never happened. So, back to part 4. This is another qualitative, observation-based argument. So the student in part 4 argues that when a wave hits a rigid barrier, the pulse reflects with amplitude on the opposite side of the original. That's actually true. So this student, I would agree with. But when a wave hits a free barrier, the pulse actually reflects with amplitude on the same side as the original wave. In this case, you could do this by putting a rod that smoothly moves up and down along this ring here. And as it slides up and down, it wants to have its amplitude max out, then return to its original position, so it won't switch to the other side. For the most part, for reflections, this difference in behavior will give us differences in standing waves between string instruments and open tube instruments, but otherwise is not going to be a huge topic that you feel like you need to memorize. Great. So, have a great weekend, guys.